Okay.
Yes.
Again, Tom and I
Mm-hmm.
have worked together for some time. Tom and I have worked together for some time, so it's a pleasure to offer you the stage. Your time is very limited, I'm afraid. You have lots more to talk about, and we've certainly already spent more time at the conference talking about your enthusiasm for machine learning than we've got time for now. But this I think you will find is quite interesting as a case where you're moving between modeling and machine learning, having experience of both and drawing on both.
Okay, thank you. So I will do this unpopular thing to stand between you and our ladies meetup, or going to a pub or going to a restaurant. So bear with me. I did cut out lots of slides. I have a feeling that it's going to be a bit shorter presentation. So I took all the math out and I took a couple of examples out. So I hope it will be a bit shorter. Most importantly, there is a paper explaining all these things I'm showing. It's still in review. It just went through first round, and I'm hoping that the reviewers are going to wake up and have a coffee before they see our paper, and that we're going to have this accepted soon. By the way, PJ, I highly recommend it. Very professional. It's the cheapest, most professional publisher I ever experienced so far. And so that's very important. So if you want to zoom in into this machine learning to spatial data, then look at the paper. It's almost now 50 pages, so it's quite extensive. And we also wrote this little tutorial, and so that's on GitHub. So the only thing you really have to take with you is the URL of the GitHub. I've been working with R for about 10 plus years, and about 5 years ago I thought let's start using R to make soil data. And we went quite ambitiously, and I wasn't sure if it's going to work, and so we did a whole world at the 250 meter resolution. So just to give you an idea, that's about 1.4 billion pixels to cover the land mask. I was afraid, was this going to work or not, and so I had to teach myself parallelization and tiling and optimizing things, and we did succeed. So we got this paper, and we got about 50,000 people downloading the data, so we made this global soil data set called SoilGrid. So I'm very proud that we did it in R. So just as an introduction, it was using machine learning algorithms in R, machine learning and spatial algorithms. So I've been working with geostatistics, and this talk is basically about spatial interpolation and spatial prediction. And I spend a lot of time, when you study, when you master degree and PhD student, then you want to master kriging, different variogram fit techniques. And so then I mastered that, and this is just 2 books I use because they have R packages in geostatistics. But so there are many more books. But so I've been using then the Ezra Pebes Magistat package and GeoR package. And that was kind of my main tool for a long time. And then I published a few, so just to give you an idea, the typical modeling in geostatistics is you determine the distribution of target variable, then you fit a variogram, you have to look whether there's an isotropy or not, then you look at the non-stationarity properties, and then you do some predictions, and you can get kriging, you can get kriging variants, and then you do some validation of the maps. And so that's a typical process of geostatistics. So that's how it looks like in GeoR. So we have to say this lambda 0, we specify that as a log normal variable, needs a transformation. Then we have to specify initial parameters of variogram, and then we have to say what type of variogram we use. So there's quite some input from the analyst. And then when we do kriging, we can also specify the search radius, and we can specify different things. So that's the typical thing you do with the kriging. Then there's a transformation, there's a back transformation afterward. So there's quite some things to do. And what I want to say, I've been working with geostatistics, and I published a few papers on this regression kriging. And you know how it goes in science. You reach a level in science when you Google some topic and you pop up as a number 1 or number 2. So that's basically you're somebody in science. So we are just scientific words really in our work. So I managed to get identified by this term regression kriging, and it became de facto a technique in many, and especially in environmental sciences, as a technique to do spatial interpolation. And so funny thing is that people now saw me and say, hey, you are the regression kriging guy, and I stopped using this method about 2-3 years ago. So that also happened in science, that you become a kind of some method becomes buried, and you're still kind of living, so, and you're associated with it. So that's very interesting, because I switched to using what I'm going to show you now. I switched to using machine learning purely also on spatial data. One of the techniques was very interested in is random forest, and also because one of the authors on the paper, and the main author of the Ranger package, which is a C++ implementation of random forest, so it's fully scalable. It's very efficient, and also it can be used to estimate uncertainty of predictions, and also it can be used to plug in lots of things. So I was interested in random forest, and you see there is a bit of change. You see less and less interest in kriging, more and more interested in random forest, at least according to the Google Trends. So the problem is when you just use random forest for spatial prediction, you have this thing that like you ignore the spatial autocorrelation. So you ignore that the points have locations, and there's some orientation between points and proximity effects. So you completely ignore them. And there's many papers they take the spatial data, they fit a machine learning model, and they do predictions, and they just ignore that. Okay, so there are many papers, but it's suboptimal, because we know, especially if there is a spatial autocorrelation, that means that the values are autocorrelated, especially in shorter distances. It means that influences the model, and so then any model that ignores that, it's suboptimal statistically. So we thought, okay, let's try with Ranger, with the random forest, also to plug in geographical distances. And so we think how to do that the best. So we came to this very actually simple system that we calculate the geographical distances to all points, either to classes of points or to each individual point. So you basically get a one raster map for one point. And then you have this generic system where we say we do a spatial prediction, where you have a geographical predictors, we have a surface reflectance predictors, and we have a process-based predictors. So that's this generic model. It's just this formula. Then it develops further in the paper, but I took it out because it's the end of the day. But this is basically the idea. And for distances, that gives you flexibility, because in machine learning you work with nonlinear models, so you don't have to use only Euclidean distances, which are the one on the left here. You can also use, with the G-distance package, you can use these complex speed-based distances, and you can use the DM and calculate all the upslope and downslope distances in a watershed. So you can plug in lots of different types of distances. And so it gives you many options. So I made this little function just to get the distances. So this is comparison now to kriging. Instead of doing kriging, I just calculate the distances, and then I do overlay points to distances, and I fit a random forest model. Actually, it's very simple, and then you do prediction. It's very simple, and this is the result. So on the left, you see the ordinary kriging in GOR, so state-of-the-art geostatistics, model-based geostatistics. On the right, you see random forest. So only geographical distances. There's no other maps or DEM or remote sensing data, just geographical distances. That's another example. Also, this is some heavy metals in soil. And you see it's also very comparable. You get this kind of smooth patterns, and you get the same places where there's a high values and low values. And there is a bit of smoothing effect of random forest, probably because it's an ensemble, so there's lots of trees. And then this is a bit more complicated example, and this is a rainfall, and this is an isotropic, and this is a famous data set used for spatial interpolation comparison. And you see what's very nice that also machine learning finds this anisotropy, but in geostatistics anisotropy you model globally. Very often you do geostatistics with this global assumption, and so this stationarity assumptions. And then what happens in random forest, because it's tree-based, it can have a local, it can be anisotropic, but it can also be isotropic. So it really locally adjusts the data. And very, very interesting is the prediction error for the random forest, which is based on a quantile regression forest, shows that much more contrast. The map on the lower right corner, it shows much more contrast. So the machine learning has spent much more time looking for where the errors are highest. So it gives you kind of additional information that I think in geostatistics we missed it. Very often we missed it because we would just get this universal Kriging variance or regression Kriging variance, which shows you usually the distance from the points. As you get further away from the points, you get high errors. This is spatiotemporal data, also very interesting. The upper one is the machine learning, and lower one is Krige ST. So this is the space of the state-of-the-art space-time geostatistics, and you see that there are similar patterns, except you can more nicely plug into the machine learning. You can plug in relief, long-term rainfall, etc. And then these things comes back because machine learning can find nonlinear relationship and can deal with all this complexity between space and time and covariates at the same time. And so we discovered, and this is again the prediction error, and also much more contrast is shown, and it can really pick up individual stations where you have like a high value. If you look at this station here, blue on the left, it's a single station where it has a high rainfall, and the machine learning picks it up multiple times as having high errors because of the due to the out-of-bag takes. It picks it up as something where it's a high error, and then it plots that error, and you can see it also even propagates through time. So that's all what I wanted to show you. So very funny, you can basically skip geostatistics. Many of my students now go and tell me, oh, we just had a module on geostatistics, and now we follow your talk, and what do we do now? We just drop that. We don't have to use that. Well, it's not completely true. You still have to understand what is spatial autocorrelation. You have to do tests. You have to plot variogram still, but it's possible that Kriging is, as a method, I think I'm using it less and less, and it can be replaced. It can be replaced by machine learning. So I would like to stop with that, and I don't think there will be any questions, but thank you for your time.
Are there actually any questions? Are there any diehard geostatisticians in the room?
We have time for questions.
Question?
We have time for questions.
Yes, there was a question here.
Do you think about incorporating some other machine learning techniques, not only random forest, but there is really big movement towards deep neural networks? So are there any plans related with that? Yeah,
that's an excellent question. So what we discussed and what we discovered that any tree-based type of statistical learner or method will work with the spatial data, spatiotemporal data. Neural nets, I'm not sure, but tree-based, absolutely, because it can really localize. You can localize spatially where you have different changes in values. So absolutely, you could probably get very similar results with the GBM and XGBoost. Now I like random forest because it also has uncertainty. I've been very critical for like 5 years ago. I was very critical. I said, machine learning, what is this? I don't know what is the uncertainty. I get the prediction, what's the uncertainty? But I want the uncertainty per prediction. That's what I was used to do in spatial interpolation. Every time I provide somebody prediction, I said this is prediction interval. And so now with Ranger, we can do that uncertainty. And it's quite robust because it's based on quantile regression, random forest. So you get not only some variance, you get a whole distribution. You can say I want 99% or 90% or 50% interval. So that's why I like random forest and Ranger. But any tree-based model, you can use it, yes. And you can do that ensemble out of tree-based.
Any further questions? Okay.
I think Gergely will have an announcement. Or
yes.
Gergely? Yes? Okay.